It's a crime, wasting time. It's a crime. It's no use of wasting time. Not putting off things for tomorrow.
In the next 3 videos, we will develop a model for the simulation of 3D aircraft motion. In 3 dimensions, the motion of a rigid body can be decomposed into the translational motion of the body's center of mass and the rotational motion of the body about its center of mass. Translational motion in 3D is governed by Newton's second law of motion, force equals mass times acceleration, exactly as it is in 2 dimensions, so there's nothing new there. Rotational motion, however, is a different story. The first problem is representing the orientation of the airplane with reference to an inertial frame of reference, which brings us to the subject of quaternions, which we will use to keep track of the orientation of the airplane in 3-dimensional space. Quaternions were developed in the 19th century as an extension of complex numbers to 3 dimensions. A quaternion can be written as A1 plus A2 times I plus A3 times J plus A4 times K, where A, 1, 2, 3, and 4 are real numbers, and I, J, and K are imaginary numbers that are all square roots of -1. I, J, and K multiply as shown on line 1. The formula for multiplying 2 complex numbers follows from the distributive law and is shown in equation 2. This is the formula we will use to write a MATLAB function that multiplies 2 quaternions, represented as 4 vectors. We want to use quaternions to rotate vectors in 3-dimensional space. A 3 vector is represented by a quaternion as shown in line 1. That is, the first component is 0, and the 1, 2, and 3 components of the vector become the 2, 3, and 4 components of the corresponding quaternion. We'll need a friendlier formula for multiplication than the one we have, and fortunately we can obtain this by inspection. Line 2 shows the right-hand side of the quaternion multiplication formula, along with a regrouping of the terms in the product. We'll let the vector n have components a2, a3, a4, and the vector v have components b2, b3, and b4. Then, notice that the terms in the product circled in red equal the dot product of the vectors n and v. The terms circled in green equal a1 times the vector v. The terms circled in pink equal b1 times the vector n. And the terms circled in blue equal the cross product of n and v. Thus, we can write the product of 2 quaternions as shown in line 3. That is, the product of quaternions a1 vector n and b1 vector v is a1 times b1 minus the dot product of n and v, followed by the sum of a1 times v, b1 times n, and the cross product of n and v. With this formula and a little geometry, we'll be able to show how quaternions can be used to rotate vectors in 3 space. So let's do the geometry. Let n be a unit vector that will be the axis of rotation. We'll rotate a vector v around n, and we'll start with v perpendicular to n. Then n cross v is perpendicular to both n and v, and these 2 vectors define a plane which is perpendicular to the axis of rotation n. Let the vector v' be the result of rotating v theta radians around n. Then v' is perpendicular to n and in the plane formed by v and n cross v. This is shown in the top diagram. The bottom diagram shows the same configuration, this time looking down the axis of rotation. The length of the projection of v' onto v is the length of v' times cosine theta. The length of the projection of v' onto n cross v is the length of v' times sine theta. Since the length of v' equals the length of v, and the length of n cross v also equals the length of v, since n is a unit vector, we have formula 1, which expresses v' as a linear combination of vectors v and n cross v. Remember this formula. A rotation quaternion is a quaternion having the form shown in equation 1, with the first component equal to the cosine of the angle of rotation, and the next three components equal to the sine of the angle of rotation times the unit vector axis of rotation. Line 2 shows the result of multiplying r theta n times the quaternion corresponding to the vector v. We'll still assume that v is perpendicular to n. Since n is perpendicular to v, the dot product of n and v is 0, and the equation simplifies as shown on line 3, which we recognize from the previous slide as the quaternion representing v prime, that is, v rotated theta radians around the n-axis. What happens if we reverse the order of multiplication? Line 4 shows that the result of multiplying on the right is the vector cosine theta times v plus sine theta times the cross product of v and n instead of the cross product of n and v. Changing the order of terms in the cross product changes the sign of the cross product, shown on line 5, and this expression is equal to cosine of minus theta times v plus the sine of minus theta times the cross product of n and v, and that equals r of minus theta n times the quaternion corresponding to v. However, if v is not perpendicular to n, then r theta n will not rotate v theta radians around n. So, we're not done yet. Any vector v can be written as a sum of vectors, one perpendicular to the axis of rotation and one parallel to the axis of rotation. If v is parallel to n, then n cross v equals 0, and the basic formula for multiplying two quaternions becomes the formula shown in line 2. And this formula is commutative by inspection. So, if v is parallel to n, then the product of r theta n times the quaternion representing v equals the product of the quaternion representing v and r theta n, as shown in line 3. Now we're ready to develop a formula for rotating vectors. Given an axis of rotation n and any vector v, v can be written as the sum of vectors v parallel, which is parallel to n, and v perpendicular, which is perpendicular to n. Let v prime be the vector v rotated theta radians around the n-axis. Since v parallel is parallel to the axis of rotation, it doesn't rotate. And line 1 shows that r theta over 2 n times the quaternion representing v parallel times r minus theta over 2 n leaves v parallel unchanged. Line 2 shows that r theta over 2 n times the quaternion representing v perpendicular times r minus theta over 2 n is equivalent to r theta n times the quaternion representing v perpendicular, which rotates it theta radians. So, r theta over 2 n times the quaternion representing v times r minus theta over 2 n equals the sum of the quaternion representing v parallel and the quaternion representing v perpendicular rotated theta radians around n. And that quaternion represents v rotated theta radians around n. We need one more property of rotation quaternions and we'll be ready to solve the orientation problem. Given two rotations, theta 1 around n1 and theta 2 around n2, the product of the quaternions representing the two rotations represents one rotation followed by the other. The expression for rotating a vector using the product quaternion is expanded on line 1. Note that the inverse of the product of any two quaternions x and y is given by the product of y inverse times x inverse. Making that substitution in line 1 leads to the result in line 2. Also note that the inverse of r theta n is r minus theta n, and r minus theta n equals r theta n conjugate. When we simulate an airplane, the forces and torques operating on the airplane are calculated using body frame coordinates. The airplane body frame consists of a roll axis along the airplane center line, a pitch axis extending out the left wing, and a yaw axis pointing up. The laws of motion apply only in an inertial frame of reference, and the airplane body frame is accelerating and rotating, hence it is not an inertial frame. In order to apply the laws of physics to calculate airplane motion, we'll need to translate the forces and torques operating on the plane to an inertial frame. Let Q be the quaternion that rotates the inertial frame to the airplane body frame, and let omega be the angular rate vector for the airplane at time t. Then we can construct a quaternion that represents the rotation the airplane will experience in the next dt seconds as follows. The total angular rate is given by the norm of omega, and the axis of rotation is given by omega divided by its norm, as shown in equation 1. The angle the airplane rotates in the time interval t to t plus dt is given by the product of the total angular rate and dt, and the quaternion corresponding to that rotation is given in equation 2. Q is updated as shown in equation 4 and represents the rotation to the body frame at time t, followed by the rotation that occurred from time t to t plus dt. One detail remains. Given a vector in B frame coordinates, what are its coordinates in the I frame? Let Q be the quaternion that rotates I frame basis vectors to B frame basis vectors. And note that we're assuming that the origins of the B frame and the I frame are the same. Suppose Q maps the vector 1, 0, 0 to ABC. Then the vector ABC in the I frame corresponds to the vector 1, 0, 0 in the B frame. Well, Q maps 1, 0, 0 to ABC. So apparently, Q maps B frame coordinates to I frame coordinates. This still surprises me. The assignment is to use quaternions to represent airplane orientation in an airplane simulator minus the dynamics, which we'll get to in the next two videos. Thus, in this simulation, velocity is constant and the angular rates are pre-programmed. The program outline that follows also has the code we'll use for drawing the airplane. First, let's have a look at what the simulation does.
Some wasting time.